In 2012, humanity achieved something remarkable, a discovery that shook the world of physics and captured global attention. Deep beneath the Franco-Swiss border near Geneva, the largest scientific machine ever built, a 27-kilometre ring buried underground, accelerated protons to unimaginable speeds before smashing them together. Out of the chaos came evidence of something extraordinary, a particle predicted half a century earlier, the Higgs boson. Headlines around the world hailed it as the discovery of the century. Some even called it the God particle, and Nobel Prizes were awarded to the theorists who had first predicted its existence nearly half a century earlier. But what exactly is the Higgs boson? Why was its discovery such a big deal? And is the boson itself really the most important part of the story, or just a clue to something deeper? And what about the Higgs field that supposedly permeates all of space? How can a simple ripple in that field show up as a particle? And what is the Higgs mechanism? This strange process that gives mass to some of the fundamental particles of the standard model. That's the challenge we're going to take on today. No analogies, no metaphors, just clear reasoning and a touch of basic calculus. I'm going to guide you through a simplified model of the Higgs mechanism, how a quantum field stretching invisibly across all space can give particles their mass, and if some all-powerful being were to switch off that field's background value, electrons, quarks, and the W and Z bosons would all become massless. Atoms could never form, no chemistry, no life, no you, no me. So yes, Higgs matters, and today we're going to find out exactly why. But first we need a strategy, a roadmap to build our intuition step by step. First, I'll remind you what a quantum field is, and how particles can be thought of as ripples in those fields. Next, we'll see how the equations of motion distinguish between massless and massive particles. Then we'll introduce the Higgs field itself and uncover the Higgs mechanism. Finally, we'll see how ripples in the Higgs field reveal the particle that was discovered at CERN in 2012, the Higgs boson. By the end, we'll see how the Higgs mechanism accounts for mass and better understand why the universe has the structure that it does. So what is a particle in modern quantum field theory? Well, a particle is the smallest possible vibration, a single quantum, of an underlying quantum field. Now, I've made an entire video on this topic for those who would like a deeper dive, but here I will give a brief overview. Broadly speaking, there are two kinds of particle, massless and massive. Each one corresponds to a ripple mode of a field and is described by a relativistic equation of motion. For a massless particle, the field equation has the following pure wave form. Here, the symbol phi is simply our label for the field, where a field is something that takes on a value at every point in space and time. Depending on the type of field, that value could be a single number, or it could be more complicated, like a quantity with direction as well as magnitude. For now, we will write our field as phi of x and t, a simple function of position and time, to focus on the essential idea. The field is the fundamental entity, and particles emerge as its ripples. Now, if we take a travelling wave solution of the form a cos kx minus omega t, where k is the wave number and omega is the angular frequency, and sub this into our wave equation, we find the following so-called dispersion relation, omega squared equals c squared k squared. Notice that as k tends to 0, which corresponds to increasing the wavelength, the frequency omega tends to 0. This is telling us that for a ripple in a field obeying this type of wave equation, there is no limit to how low the frequency can be. Now compare this with a slightly modified wave equation, which has an additional restoring term. If we sub in the same travelling wave solution, we arrive at a modified dispersion relation. Here the behaviour is different. We see that as k tends to 0, the frequency does not vanish, but instead tends to omega naught. This is telling us that for a field obeying this modified wave equation, there is a minimum possible frequency of vibration. And so in summary, we have two possibilities. One wave equation with a dispersion relation with no minimum frequency, and one modified wave equation with a modified dispersion relation which does have a minimum frequency. And we can see this even more clearly if we plot a graph with k on the x-axis and omega on the y-axis. And if we then plot the unmodified dispersion relation, we see that as k goes to 0, so does the angular frequency. Whereas if we plot the modified dispersion relation, as k tends to 0, the angular frequency tends to omega naught at k equals 0. To see what this means for particles, we first need to quantize the field and then compare these dispersion relations with the Einstein energy-momentum relation. The critical link is that when a field is quantized, each allowed ripple mode behaves like a quantum harmonic oscillator, and the energy of one quantum of vibration is equal to h bar omega. So if we take the modified dispersion relation and multiply through by h bar squared, we obtain the following expression, and then using the fact that E equals h bar omega, we can write this in a form that looks structurally similar to the Einstein energy-momentum relation. The comparison is striking. We can make the match exactly if we identify P equals h bar k and m equals h bar omega naught divided by c squared. So the quantum of this modified field behaves exactly like a relativistic particle with momentum p and mass m. And we see that the minimum frequency, omega naught, determines the mass of the quanta of the field. Okay, so the modified wave equation describes a field whose quanta behave like massive particles. If we now consider setting omega naught equals to 0, then we get the unmodified wave equation, and we see that the mass term reduces to 0. The quanta of fields obeying the unmodified wave equation are massless particles. And this is the basic structure that we will be using. The unmodified wave equation describes vibrations that have no minimum frequency and the quanta of the field are massless. The modified wave equation corresponds to vibrations which have a built-in minimum frequency omega naught, and the quanta of the field are massive with mass equal to h bar omega naught divided by c squared. But in writing down the modified wave equation, we simply inserted omega naught by hand. But where does such a term really come from? This is where the idea of a potential becomes essential. A term in the field equation that is directly proportional to the field itself, like the restoring term in the modified wave equation, can be traced back to a potential function associated with the field. To see how this works, recall the case of a spring with a mass attached. There the potential energy is given by half kx squared, where k is the spring constant and x is the extension of the spring, and the restoring force, which shows up in the equation of motion, is related to the derivative of the potential function. And if we sub in the potential function, we get the standard Hooke's law result, minus kx, telling us that the force is proportional to the extension, but in the opposite direction. The key point is that the restoring tendency comes from the gradient of the potential function. When x is negative, the slope is negative, and the minus sign makes the force positive, back towards the equilibrium. However, when x is positive, the slope is positive, and the minus sign makes the force negative, again back towards the equilibrium. At all stages, the force is directed so as to restore the spring to its equilibrium position. Now, for a field phi, the story is conceptually the same, except we don't talk about a literal force on a mass. Instead, the equation of motion contains a restoring term that comes from the gradient of a potential function, v of phi. To make this concrete, let's look at a simple quadratic potential function, half omega naught squared phi squared, which mirrors the quadratic potential function for an oscillating spring. If we then differentiate this with respect to phi, we find omega naught squared phi. Subbing this into the equation of motion recovers exactly the modified wave equation we encountered earlier, and so we see that the mysterious omega naught squared term we had before isn't arbitrary. It comes directly from choosing a quadratic potential. Now, the first thing to appreciate is that a field left to itself will naturally settle into whatever value minimises its potential. It's just like a spring. The mass rests at its natural length, where the potential slope is 0 and the restoring force disappears. And it then follows that the resting value v is the place where the gradient of the potential is 0. In other words, where dv by d phi, evaluated at phi equals v, is equal to 0. And from now on, we will use prime to denote a derivative with respect to the field. and so the condition becomes v prime of v equals 0. Once we know the resting value, the next step is to ask what happens if the field is nudged slightly away from v. To make this precise, we write the field as phi of xt equals v plus h of xt, where v is the resting value of the field and h of xt is a tiny disturbance on top of it. In other words, v tells us where the field sits on average, filling all of space, while h of xt captures the small wiggles that can travel through it. Those wiggles, when quantized, correspond to the quanta of the field, the particles. Okay, so what happens to our equation of motion once we rewrite phi in this way? And note that we are now writing the equation in its general form, where the restoring term is written as the derivative of a potential function. Well, if we sub in phi equals v plus h, we find the following blue expression. And then, because v is a constant, the derivatives only act on h, and we end up with the following equation. Okay, so how do we deal with the potential term? Well, we can perform a Taylor expansion around v, the constant background value of the field, in which case we can write v prime of v plus h is roughly equal to v prime of v plus v double prime of v times h, plus higher order terms. And then, since by definition the gradient of the potential is 0 at v, we can write v prime of v plus h is roughly equal to v double prime of v times h. If we then sub this back into our equation, we find that the equation of motion for our ripple h takes the following form. And this has exactly the same form as the modified wave equation that we've already seen. Only now we note that the coefficient of the restoring term is not just some arbitrary parameter we inserted by hand, it is the curvature of the potential at the resting value. In other words, v double prime of v. And because we already showed that the mass of the quanta in such a wave equation is set by the restoring coefficient, we can now express it more generally as m equals h bar times the square root of v double prime of v divided by c squared. In other words, the mass of the field's quanta is determined directly by how sharply curved the potential function is at its minimum. To check how this all fits together, suppose the potential is this simple quadratic function that we looked at earlier. Then, if we differentiate twice, we end up with omega naught squared. And the general mass formula then reduces to h bar omega naught divided by c squared, which is exactly the result we obtained earlier. And so here is the deep principle. Whenever a field obeys a wave equation of this type, one with a restoring term derived from a potential, and has a stable resting value v, the mass of its quanta is determined by the curvature of that potential at the resting value. And so we see that a sharply curved potential corresponds to a more massive particle, whereas a shallow broad curved potential corresponds to a less massive particle. And if the potential is completely flat at the resting point, then v double prime of v is equal to 0, there is no restoring term at all, and the quanta of that field are massless. So we can boil all of this down to two simple rules. Firstly, the first derivative of the potential tells you the resting value of the field, v. In other words, v prime of v is equal to 0. The second point is that the second derivative of the potential at the resting value allows you to determine the mass of the field's quanta. But in the real standard model, things are more subtle. Most particles don't get their mass from the curvature of their own potential. Instead, they acquire mass by interacting with another field, the Higgs field, which itself has a non-zero average resting value across all of space. Ever get that itch to crack a puzzle that nobody else can? I thought I was just picking up a guide to rebuilding civilization. How to generate electricity from scratch, purify water, or even recreate old technologies. But as I read on, I realised the book is hiding something else entirely. Flip through and you'll spot tiny butterflies in the margins. At first they look like harmless decoration, but they're signals. Each one marks an entry-level riddle, and solving the first few leads somewhere unexpected, a hidden website. The opening puzzles are warm-ups, simple ciphers, patterns, a bit of code breaking. Exactly the sort of thing that keeps a physics brain buzzing at 2 a.m. And then it escalates. The deeper you dig, the more layers appear, puzzles tucked inside diagrams, symbols that repeat when you least expect them. And here's the wild part. So far, only 7 people on the planet have solved every layer. Just 7. Anyone who completes the whole quest is welcomed into something called the Order of Seekers, along with a real-world reward from the creators. But the quest is only half the story. Even if you never solve a single riddle, the book is still a joy to explore. Every spread is crammed with rich illustrations, clever references and Easter eggs. I especially love the chapters on optics and electricity, which tell the story behind some of the world's greatest inventions, plus a few sly pop culture nods. As someone who spends a lot of time explaining physics, I found it fascinating to see those concepts broken down in such a different context. It's the kind of book you keep coming back to, something you can pull off the shelf to spark a conversation, to learn something new, or to gift to anyone with a curious mind. So whether you're chasing puzzles or just geeking out over the beautifully explained science, the book is worth getting lost in. To see how this mechanism works in the simplest way possible, let's consider 2 fields. The first, which we'll call phi, has a potential function that makes it settle into a non-zero average resting value, which we'll call v. The second, chi, will be described by the unmodified wave equation and therefore have massless quanta. And we'll now let these 2 fields interact with each other. When 2 fields are present, the potential function is equal to the sum of 3 contributions: phi's own potential, chi's own potential, and their interaction potential. The equations of motion for each field follow the same rule as before: the unmodified wave equation plus the slope of the potential along that field's direction. So for the phi equation, we have the following purple expression, and for the chi equation, we have the following blue equation. And we see that both depend on the derivative of the total potential function, and therefore both are influenced by the interaction potential. So what form does the interaction potential take? Well, a natural choice for this interaction is a term with the following structure, where g is called the coupling constant, and this sets the strength of the interaction. This potential is quadratic in both phi and chi, and it has 2 important features. First, it vanishes whenever either field is 0, so it only switches on when both fields are present. Second, once phi acquires a non-zero average value v, the interaction produces a mass term in the chi field equation of motion, as we will shortly see. With this choice of potential, it then follows that the derivative of the total potential with respect to chi is equal to u prime of chi plus g squared phi squared chi, and the derivative with respect to phi is equal to v prime of phi plus g squared chi squared phi. And if we then sub these relations back into our earlier field equation expressions, we find that the phi and chi field equations take the following form. And now comes the crucial step. To set up the Higgs-style mechanism, we make 2 deliberate choices. First, we take the chi field to be massless on its own by setting its potential u of chi equal to 0. In other words, we force the chi field to have no quadratic potential term, and hence no curvature, meaning no mass term, which means that by construction, the quanta of the chi field are massless. In this case, u prime of chi vanishes. Second, we choose a potential v of phi that makes phi settle into a non-zero resting value v. We begin by looking at the chi equation of motion. First, note that if phi were to settle into a resting state with an average value of 0, then the interaction term would vanish and chi would obey the unmodified wave equation describing a field with massless quanta. By contrast, if phi settles into a state with a non-zero average value v, then the chi equation takes the following form, now containing a term linear in chi with both g and v constant. Now, the structure of this equation should look very familiar. It has exactly the same form as the modified wave equation we explored earlier, corresponding to a field with a quadratic potential and quanta with mass. The extra term, proportional to chi itself, fixes a minimum frequency of oscillation of the chi field, And just as before, when we quantize those ripples, the minimum frequency appears in the mass equation. Explicitly, we have that m of chi is equal to h bar gv divided by c squared. And so we see that chi, which began as massless, has now acquired a mass. The mass wasn't put in by hand, it emerged automatically from phi's non-zero resting value and the coupling between the two fields. But that immediately raises the next crucial question. What exactly fixes the resting value v of phi in the first place? Earlier, we said that a field's resting value is determined where the slope of the potential vanishes. In other words, where v prime of v is equal to 0. So the answer must depend on the form of the potential function v of phi. Okay, so let's begin by testing a simple quadratic potential like we encountered before of the form half omega naught squared phi squared. If we then differentiate this function and set the result equal to 0, we see that there is only one stationary point corresponding to phi equals to 0. In other words, with a quadratic potential, phi always wants to rest at 0. But if phi rests at 0, then the interaction term g squared phi squared chi in the chi equation of motion vanishes, and chi never acquires a mass. So the quadratic case cannot give us what we want. We need a different potential, one that forces phi to settle into a non-zero value v. So the question is this: can we design a potential v of phi that makes phi naturally choose a non-zero value v? In other words, instead of the resting state being phi equal to 0, could the resting state of the field lie away from 0? Well, the answer is yes. The simplest and most famous example is the so-called Mexican hat potential, which takes the following form, where mu and lambda are both constants and both mu squared and lambda are greater than 0. At first glance this looks strange. The quadratic term has a negative coefficient, which means that near phi equal to 0, the potential curves downward instead of upward. Left on its own, that would make the system unstable, like balancing a ball on top of a hill. But the quartic term, which is positive, takes over when phi is large and makes the potential rise again. Together, these two terms create the familiar hat-like shape, a central peak at the origin and valleys away from 0. I'll refer to this as the Mexican hat potential throughout the video, since that's the common term in the literature. Strictly speaking though, in our toy model with a single real scalar field, we're just looking at the one-dimensional double-well slice of that potential. We can see this most clearly by plotting the potential function with phi on the x-axis and the potential on the y-axis, and we see the characteristic shape appear. Okay, so what is so special about this particular potential function? To answer that question, we need to find the stationary points of the function, the places where the slope of the potential vanishes. In other words, we need to differentiate the potential with respect to phi, in which case we find minus mu squared phi plus lambda phi cubed, and then we need to set this equal to 0. If we then factorize this expression, we see that the stationary points occur when either phi equals 0 or when the term inside the bracket equals 0, which corresponds to when phi squared equals mu squared over lambda, which implies that there are stationary points at phi equals plus or minus mu divided by the square root of lambda. Now, it is customary to define v equals mu over the square root of lambda, in which case our stationary points occur at phi equals 0 and at phi equals plus or minus v. Okay, so now we found the stationary points of our Mexican hat potential, but how do we know whether these stationary points represent minima? To answer this question, we need to check the curvature of the potential and see whether it is positive or negative. If we take the expression we calculated earlier for the first derivative of the Mexican hat potential, and then differentiate again, we find minus mu squared plus 3 lambda phi squared. We can then check each of our stationary points. At phi equals 0, we find that the curvature is equal to minus mu squared, which is negative. On the other hand, at phi equals plus or minus v, we find that the curvature is equal to 2 mu squared, which is positive. And so we see that at phi equals 0, we have negative curvature, which means a maximum, an unstable hilltop. On the other hand, at phi equals plus or minus v, we have a positive curvature, meaning these field values represent minima, and therefore phi equals v represents a true resting value of the phi field. In other words, the potential is minimized when the field sits at a non-zero average value equal to v. And we can visualize this. Although there is a stationary point at 0, it's unstable, and any small perturbation will cause the field to settle into one of its true minima at plus v or minus v. In the animation, we have shown the field settling at plus v, but the physics would have been identical if the field had settled at minus v. And the fact that the field settles into a non-zero average value represents a crucial departure from an ordinary quadratic potential. As we've already seen, for a simple quadratic potential, the resting state of the field lies at phi equals 0. But for the Mexican hat potential, the resting value of the field lies away from 0 at phi equals plus or minus v. The field doesn't want to sit at the origin. It naturally rolls off the hilltop and settles into one of the valleys. Okay, so let's now see what this does to our coupled equations. Recall that Chi's equation of motion included the interaction term g squared phi squared chi. Now, if phi sits at its resting value v, then this interaction term becomes g squared v squared chi, where v is a constant. The equation now has exactly the same form as the modified wave equation we looked at earlier, and upon quantizing the field, we identify the mass of the chi quanta as h bar gv divided by c squared, following the same steps as before. And we can see clearly from the mass equation that if either v, the resting value of the phi field, or g, the coupling between the phi and chi field, were 0, then the quanta would be massless. And here is the key point. The chi field had quanta that started out massless, yet once it interacts with phi, and phi settles into a non-zero resting value v, the chi quanta acquire a mass automatically. The mass is not something we had to insert by hand, rather it emerged from the interaction with the background value of the phi field. And this toy model captures the essence of what physicists call the Higgs mechanism, mass emerging when a field with a non-zero background value interacts with other fields. In the full standard model, the very same principle underlies how the Higgs field gives mass to the W and Z bosons, quarks and leptons. Okay, but what about phi itself? We have seen that the interaction with chi gives rise to a mass term in chi, but what about the quanta of the phi field itself? Are the quanta associated with the phi field massless or massive, and how can we tell? To answer this, we need to look at what happens when phi is nudged slightly away from its resting value v. To do this, we focus on the phi equation of motion, and if we explicitly sub in the derivative of the Mexican hat potential, we end up with the following equation of motion for phi. Now, here is the idea that we touched on earlier. We want to look at small fluctuations of the field around its resting value. To do this, we write phi of xt equals v plus h of xt, where v is the resting value of the field, and h of xt represents the ripples around it. We then substitute this into the phi equation of motion. Then, because v is a constant, any derivative acting on v will give 0, and so the only derivatives that survive are those acting on h. And so, as a result of the substitution, the first term in the equation becomes d2h by dt squared. In the same way, the second term in our equation ends up being equal to c squared d2h by dx squared. Okay, so that's the derivative part. But what about the term corresponding to the derivative of the Mexican hat potential? Well, if we replace phi by v plus h, we find the following result. And then expanding out the brackets, we find this messy looking purple expression. However, it's not as bad as it first looks. We can simplify matters by using the fact that v equals mu divided by the square root of lambda, which we established earlier when minimizing the Mexican hat potential. In which case, the first bracket vanishes and the second bracket simplifies to 2 mu squared. And so, when the dust has settled, this term takes the following form when expanded in terms of the ripple h. And then finally, if we look at the interaction term and replace phi with v plus h, we find the following expression. And when we expand out the brackets, we get g squared chi squared v plus g squared chi squared h. If we then pull all the different pieces together, we end up with the equation of motion written entirely in terms of the fluctuation h. Okay, let's pause and take stock of what we've done so far. If you recall, the phi field doesn't rest at zero. Rather, its potential forces it to settle at some non-zero value v. We then wrote phi equals v plus h, where h is a small ripple around that resting value. The chi field, by contrast, does rest at zero, since, if you recall, it was chosen to have no potential of its own. And therefore, any appearance of chi in the equations is already a small fluctuation away from the field's zero average rest value. And so, in this equation of motion, both h and chi represent tiny disturbances around their respective resting values. To keep track of this, imagine each factor of h or chi is of size epsilon, where epsilon is very small. Then any term in the equation containing a single h or chi counts as order epsilon, whereas terms like h squared or chi squared count as order epsilon squared, and terms like h cubed or chi squared h are order epsilon cubed, and so on. With this in mind, let's look again at our equation of motion. The term 2 mu squared h is linear in h, so it's first order in epsilon. That's the leading effect. All the other pieces, h squared, h cubed, chi squared h, involve higher powers of small fluctuations and are therefore higher order in epsilon. They're certainly real, but they are suppressed when the ripples are very small. And so at leading order, we can ignore them. And what remains is simple, elegant, and powerful. This is the equation we've been working towards all along. And here is the reveal. This equation describes ripples, h, around the average value v of a field that permeates all space. That field is the Higgs field, and those ripples, when quantized, are the Higgs bosons, the very particles whose discovery in 2012 confirmed this entire framework. After all the algebra, after all the abstraction, we've arrived at the real physics. The Higgs boson is nothing more and nothing less than a quantum of vibration of the Higgs field, a field that permeates all space with a non-zero average value. And notice something striking. This equation has exactly the same form as the modified wave equation we studied earlier. The parallel is exact, which means we can now simply read off the mass in precisely the same way. And when we do, we see that the quanta of the Higgs field, the Higgs bosons themselves, have a mass given by the following expression. And here's the beautiful part. Back when we first introduced the Mexican hat potential, we saw that the resting value v of the field comes from where the slope vanishes. But if we go one step further and calculate the second derivative of that potential at the resting value v, we find something remarkable. The mass of the Higgs boson can be written directly in terms of the curvature of the Mexican hat potential at the resting value of the field. In other words, the mass of the Higgs boson is determined by the curvature of the Mexican hat potential at its minimum. And we can make this even clearer with a series of plots. We first sketch the Mexican hat potential in the first subplot. Next, we plot its slope in the second subplot and mark the points at plus v and minus v where the slope is 0. Those are the average resting values of the Higgs field. Finally, we take the slope of that slope, the curvature, and this is what you can see plotted in the rightmost subplot. Now, if we allow the steepness of the Mexican hat potential in the first plot to change, we can see the effect this has on the slope and curvature at v, and this will therefore have an influence on the mass of the Higgs boson itself. We can see this connection more clearly if we place a plot of the curvature next to a plot of the Higgs mass, As the curvature increases, the mass increases with it. That is the unifying idea. The overall shape of the potential fixes where the field settles, and the curvature of that shape at the resting value determines the mass of the ripples, the Higgs bosons themselves. So the natural question is, what actually controls the shape of the Mexican hat potential? Well, if you recall, the Mexican hat potential has the following form, and we see that its shape is controlled by mu and lambda. And by locating the minima of this function, we found earlier that the minima occur at v equals plus or minus mu divided by the square root of lambda. This means that once the resting value of the field v is known, knowing lambda allows you to determine mu and vice versa. Now, it's interesting to note that the resting value v was already known before the Higgs boson was discovered. Physicists had inferred this from precision measurements involving the weak interaction. However, what was not known was the value of lambda, or equivalently mu, and therefore the Higgs mass itself. As we've already seen, the mass of the Higgs boson can be written in terms of mu, and then using the relation between v, mu and lambda, this can be equivalently expressed in the following way. And so, although the resting value v was already known experimentally, the steepness of the Mexican hat potential, set by lambda, was not. And because of that, the precise mass of the Higgs boson could not be predicted in advance. Until the particle was finally observed, the true shape of the Mexican hat potential remained hidden. And that's where the theory left us. The equations told us the Higgs boson had to exist. They told us how its mass would depend on the curvature of the potential, but without knowing lambda or mu, no calculation could reveal the mass. The only way forward was to experimentally measure it. And that moment came in July 2012. At CERN's Large Hadron Collider, two vast experiments, ATLAS and CMS, saw the same thing. A brand new particle, appearing with a mass of around 125 GeV/c², a tiny bump in the data, signalling the discovery of a particle that had been predicted half a century earlier. It was the missing piece that fixed lambda and mu, and hence the steepness and curvature of the Higgs potential, uncovering the hidden landscape that underpins the standard model of particle physics. Now, it's important to note that in telling this story, we've massively simplified the full theory using a toy model with two simple real scalar fields phi and chi. This let us isolate the core mechanism without being buried in the full complexity of the standard model, and hopefully built some intuition about the Higgs mechanism. Along the way, we also simplified some steps. For example, when we wrote down the Higgs field equation of motion in terms of the ripple h, we deliberately set aside higher order terms that describe the Higgs interacting with itself, and other terms that show how it couples to the quanta of the chi field. In the full standard model, interactions of this kind are essential and govern how the Higgs couples to the W and Z bosons, to quarks and to leptons, the very particles that make up the matter around us. It's also important to stress that the full picture is far more intricate than the stripped down version told here. The true theory weaves together gauge symmetry, spontaneous symmetry breaking, and the mathematics of complex scalar fields, vector fields and spinor fields. And the Higgs mechanism is not responsible for giving mass to all particles. Photons remain massless, while composite particles such as protons and neutrons gain most of their mass from the binding energy of quarks and gluons in quantum chromodynamics. But by working with this simplified toy model, we've been able to uncover the essence of the Higgs mechanism, the idea that the masses of the elementary particles that couple to the Higgs field are not put in by hand. They emerge when the Higgs field acquires a non-zero resting value and couples to those fields. And the quanta of that field are the Higgs bosons, the very particles discovered at the LHC in 2012. And the discovery of the Higgs boson is a story in itself. How do you actually create and then detect a ripple in the Higgs field? And how do you find it hidden in the chaos of proton-proton collisions? That will be the subject of the next video in this series. where we'll move from equations to events, from theory to experiment, and watch how the Higgs field finally revealed itself. But for now, I just want to say thank you for watching, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much, I couldn't do it without you.